In this module, we will be giving introduction to linked lists. First, we will be talking about arrays and their drawbacks. Then, we will introduce to the linked lists. And then, we will be talking about complex linked lists. Arrays are normally called as linear lists. The assumption is the next element in the data structure is implicit in the index. Main advantage of arrays is that we can access the required element just by simply presenting its index. For example, if we assume that we have a one-dimensional array with the name element. In that one, we are assuming that the variables or symbols A, B, C, D, E are stored. Then, if I wanted ith element, for example, element of 2, that is symbol C, element of 3, symbol D. So like that, the elements of the array can be accessed straightforwardly. Of course, it's out of discussion. However, I wanted to remind you this one. In languages such as C, C++, etc., array name itself is the pointer to the array. So when I say element of I, the element, that attribute name, array name, is itself indirectly referring to some memory cell number, plus I, so is done background, and thus the required element's address is calculated, and then that element will be given to us. Like this, inside the actual operation will be like this. But however, as a programmer point of view, he will be just simply required to know that if he wants third element, simply array name in the square brackets 3. If he writes it, he will be getting that element. Like this, understanding is somewhat easy in the case of arrays. Of course, there are many ways of storing the data in the arrays. Different languages supports different style of storage mechanisms. Remember that we have discussed about row major auto storage, column major auto storage in the previous lessons. And depending upon the requirements, the programmer would like to store the data according to his wish. Probably he wants to store the data from left to right or right to left, or he wanted to store values in every alternative element only. So the way he likes, he can maintain the data in the array. But while accessing, he will be using the index of the data item, whatever he wants. Main drawback of the arrays is adding and removing elements from the arrays. For example, let us assume that we have an array with elements A, B, C, D, E in the array elements. Now we wanted to insert G at location 1. If we wanted to do so, we have to move all the other elements such as B, C, D, E by 1 unit towards right, and then at the place location 1, G can be stored. Thus, the operation, that is insertion operation, become little costly. Computational point of view, it is costly. Similarly, if I wanted to remove, then there will become an empty space in the array. So to fill that gap, we may require to move the elements towards leftwards direction. That also may be little costly affair. These are the important drawbacks of array, that is linear list. In addition, array has another evident drawback. I'm sure that most of you remembers that in C language or C++, while declaring the arrays, we have to give constant. For example, integer a of 10, which means that it allocates memory sufficient to store 10 elements. That way we are supposed to tell a constant as the array size. If we have taken the array size as 10, we can store at most 10 elements only. But in some applications, this may become a problem, especially in environments where the elements may become more than 10. Sometimes they will be less than 10. So the problem may require a dynamic dealing. Sometimes there may be more than 10 elements. You are required to store them. Sometimes only 2 elements will be there. You may require to store them also. So if we wanted to take care of such a situation, we may have to take an empty array, another 2 array, which is whose size is larger than the current array, and copy all the elements of the current array to the new array, and remove the memory of that new array, old array, current array rather, and make this new array as the current array. So it requires a lot of efforts to increase the size of the array or to let some more elements to be stored in the array. So this is the another important drawback of the array based applications. Linked lists are used in practice to take care of these drawbacks of the arrays. Evidently, the basis for linked list is self-referencing structures. Self-referencing structures contain a pointer member that points to a structure of the same structure type. For example, let us take, in the slide we have shown a structure struct node, int data, struct node star next. So here in that node, rather I say in this structure, we are having 2 data members. One is an integer type of data member known as data. Another one is next. It is a node type of pointer variable. Next is a pointer member that is supposed to point to a data structure of the same type as the one being declared. Usually this next is normally referred as a link. That is, through this we can tie this node with the next node. Like this, by linking set of these nodes, we get a linked list structure. Rather, I say that this concept is the one which is mostly used in many of the applications such as linked lists, queues, stacks, trees, graphs. In many applications, the concept of link is the basis. All operating system concepts are realized using these concepts. There are many practical systems where the concept of link is the only solution to be employed. So in the following slides, we try to give emphasis for this concept first. For example, consider the following slide. Here we have a linked list of two integers. The node type of structure which we have defined in the previous slide we have used here. The first node contains 15 and the next node address as the data member of it. Thus the arrow is used to show that the next data member of this first node is pointing to the next node. However, the last node, that is the node having 10, it will be having next value as 0 or null. One has to remember that not setting the link in the last node of a linked list to null can lead to runtime errors. One has to be very cautious while using this concept while developing the linked list based solutions. In principle, we have variety of linked lists are available. A linear list is a data structure in which each node or element will be having one unique successor. Such a type of structure is called as linear linked list. In summary, linked list is a linear collection of self-referential objects called nodes. They are connected by pointer links, accessed via a pointer to the first node of the list. Subsequent nodes are accessed via the link pointer member of the current node. The link pointer in the last node is always set to null to mark the end of the linked list. The main advantage of this linked list over arrays is that anytime we can add any number of nodes also we can go on add. Of course, only the limitation is available virtual address space in current days virtual memory systems. At the same time, anytime we can remove an object. We need not require any movements of the elements. Simply we require some adjustments of the pointers only. Whereas in the case of arrays we said or we understood that I wanted to remove one element, then all the elements or remaining elements, right hand side element has to be moved towards left side by 1 unit to fill the gap. Similarly, you wanted to insert, then first you have to move all the elements to right by 1 unit and make a space for the new object and insert that new object in that place. Especially some applications, practical applications, where we do not know in advance how many items or objects to require to be maintained. In that situation, linked lists are the best preferred ones compared to arrays. As arrays, we already understood that changing the array size, it itself requires more efforts. Whereas here, adding one more element or 10 more elements is not at all a difficult task. In general, we have some common operations on the linked list, such as creating a linked list, inserting a node into the linked list, deleting, searching for an item, retrieving, and destroying the list. The following table displays or compares the computational complexity of arrays and linked list on various operations. For example, finding list length. In array, order of complexity 1, whereas in the linked list it is order of n. Inserting a new item, here it is a order of n, whereas linked list just order of 1. Deleting the last item, so array requires order of 1, whereas linked list requires order of n. Like that, we have compared the what you call arrays and linked lists on variety of operations. This is another example to demonstrate a linked list having integer numbers. Some more examples are included in the slides for the purpose of understanding. This slide demonstrates how to delete a node from the linked list. General lists are the ones which doesn't have any restrictions on where a new item can be inserted or from where the item to be deleted. Also, which operations can be used are also not fixed. We can do load of operations on the general list. Whereas restricted lists are the ones data can be inserted and operations are performed only at one or two ends of the list. Again, we'll be having variety of general lists like random list and ordered list. In the random list, the items available or maintained in the list are not in any order. Whereas in the ordered list, the items are maintained in some order, either based upon some key. For example, if you maintain numbers, they are maintained according to the key, or they are maintained based upon the serial numbers or names, etc. Similarly, for example, restricted list, for example, good examples are queues and stacks. Queue is the one in which objects are added at one end and removed at the other end. Whereas the stacks where the objects are added one end, from the same end the objects will be removed. That is, queue is called as first in, first out. The object which is added first, that is the one going to be removed first. Whereas the stack is called as last in, first out. That is, most recently added object that is going to be removed from the stack first. Last in, first out. Probably you might have come across these words elsewhere in the studies. Or rather I say we'll be having separate lessons on the queues and stacks. There we'll be talking more about queues and stacks. We do have another type of list known as generalized lists, which are the ones in which individual list items or nodes may have sub-lists. Similarly, we do have another type of list known as shared lists, where more than one record can point to another record or sublist. Random list is the one where insertions can be made at the beginning, the middle, or the end of the list. Whereas the ordered list, the data must be inserted so that the ordering of the list is maintained. In principle, while developing linked list, depending upon the application, we will be employing variety of structures as the nodes. For example, in the previous discussions or previous slides, we have defined a node, struct node, int data, struct node star next. That is, it contains an integer member and a pointer to the same type of structure, as shown in the slide again, in current slide, first figure. Even we can have a node with 3 data fields. A node can have a structure and also again a pointer or a link. Like this, we can theoretically have any type of node. But the link is the most important aspect. That is the one, that is self-referencing. That is the one important aspect is one has to remember, one has to know while developing the linked lists. Commonly, variety of approaches are employed in developing linked lists. Some people will be having a one type of data structure for data nodes in the linked list. They are the real nodes which contains the straight information which we are interested to manipulate. And for the linked list, we may be having another structure known as head structure. It is not essential that everyone should have this approach, but we are discussing such an approach is also possible. For example, the head structure, here we are using 2 data members. One is count, other one is a pointer, that is head, which may point to the node type of object. Whereas our struct node is as it is. And also in the node structure, we need not be always required to maintain only integers. You can maintain float, you can maintain names, you can maintain anything. We can even maintain another data structure, another structure also. So the head structure, usually the count field may be used to indicate how many elements are maintained, nodes are maintained in the linked list. If that is available in the head node, then just knowing how many elements are there in the linked list is a straightforward approach. Otherwise, we may require to traverse the entire linked list and find out how many nodes are there. That is the reason why this node head structure is defined like that. It is not mandatory that we should follow that structure. We can have our own structure also. According to our convenience, we can define. Now let us have a small briefing about how to create a list. Here we assume that we have 2 types of structures. One is head structure and another one is node structure. So before creating a list, the head data members, that is count and head data members or head node data members, they will be uninitialized. That is the reason why in the slide we are shown with the question marks. When the list is created, then the head list.head is equal to null, list.count is equal to 0 statements will be executed. Thus count value becomes 0, which means that as of now, though list is available, no elements are there. Thus the head is pointing to nothing. Thus head value is null. So to insert an object, we shall allocate memory for the new node and then point the new node to its successor point the new node's predecessor to it. Let us assume that we wanted to insert a new node in the linked list. Currently, the linked list is empty. That is, list.head value is null. List is just created. We have explained in the previous slide what action takes place when a list is created. That is, count value will be initialized to 0, head value will be initialized to null. Currently, head value is null. So when we want to insert a new node is created. P new is made as pointer to that new node. Then P new arrow link is equal to list.head is executed. That is, link value of the new node created becomes 0. And then list.head is equal to P new is executed. That is, the head will be now pointing to this newly created node. Let us assume that we want to insert a new node at the beginning of the already existing linked list. Currently, head is pointing to a node in which number 75 is there. Now we want to insert 39. That is at the beginning of the linked list. That is before 75. So for this, first we create a node such that it contains a number 39. The pointer variable P new will be made to point to this node. And then the statements P new arrow link is equal to list.head is created. Currently, list.head is pointed to the node having 75. Thus, the node having 75 becomes next to this new node. And then the statement list.head is equal to P new is executed. Thus, the new node, whichever we have created, that is 39, that becomes the head of the linked list. You can see the slide where we have done the adjustments. Let us assume that we want to insert a new node, but in between a linked list. Already the linked list is having numbers 39, 75. Now I wanted to insert 52. The 52 I want to insert between 39 and 75. If that is the situation, first we have to find out the node for which this new node is going to be next node. So that we have to find out. That is done by traversing the linked list from the head node to till we find out a node whose value is, or rather I say we wanted to maintain the numbers in the ascending order. So we have to find out the node after which you wanted to insert the number 52. So now we traverse and we find out that as 52 is more than 39, so we have to insert after that. So we take a pointer P pre which points to 39. That is after 39, after the node having 39. After that we have to insert. So to do that one, so what we do is, currently the next node for the node having 39 is the address of the node having 75. So that we will make it as the next to the newly created node having number 52. That is, P new arrow link is equal to P pre arrow link. So that address we store in the new node. And then this new node will be made as the next node for the P pre. That is for 39. So that is P pre arrow link is equal to P new is executed. Thus, the 52, that is new node having 52 will become inserted between 39 and 75. You can verify the slide for the more details. Similarly, we wanted to insert a new node at the end of the list. This also can be done same as the previous fashion. That is, we traverse from the head of the linked list till we encounter either end of the linked list or a node whose value is, after which we wanted to insert the number or new node. So now in this example, the number value 134 we want to insert. So that is, it has to be inserted after 75. Thus, the node having 75 will be made as P3 and the same statements will be executed such that the new node 134 will be added at the end. Similarly, sometimes we wanted to remove the nodes having a given number, or some node we wanted to remove it. So we have to make sure that before removal, rather say after removal, the linked list has to be maintained, and also the node which we wanted to remove, for that memory also has to be deallocated. So thus, first we have to find out the node which we wanted to remove, and its predecessor also we have to find out. Then before removing this node, we have to make this node's next node as its predecessor's next node, and then this node can be removed. Let us assume that the node which we wanted to remove is just at the top of the linked list, that is the first node itself. If that is so, simply we take a pointer, we will make it point to the topmost node, for example in this case 39. So its link, that is its next node address, is now assigned to head, and then the data member, or rather I say the node which is pointed by the ploc will be deallocated by calling the function such as free. Let us assume that we wanted to deallocate the node having 52. That is, we are considering the pointer ploc is pointed to that node. So that one we want to remove. But before removal, we have to assign the next node address, that is ploc arrow link, that we have to make it as the next value for the previous node of this ploc. That is p3 arrow link is equal to ploc arrow link. That link has to be adjusted. And then the node pointed by the ploc has to be deallocated. Verify the slide where you find that a new link is created, a new arrow is shown, and then the node will be deallocated. Another type of operation which we may commonly require on linked list is searching for an object or an element. It may be possible that the list may be sorted or unsorted. However, we have to traverse each node element by element, that is node by node, and each node the content we have to verify and compare the same with the what we are looking for. Accordingly, we have to find out the node which we are interested. It may be possible that the required node can be the first node itself, or it can be in the middle, or it can be at the last also. Sometimes it may be possible that the required node may not be there at all in the linked list. It may be possible that once we find out the node of our interest, we may require to access the data in it, such as, for example, data variable of the node which we have defined in the previous slides. So that value we may require. Or something else, if you were to maintain names, ages, roll numbers of the students, then we may require that information. So accessing that is called as retrieving the data. Typically, the following code fragment will help us to traverse the string from the head node till we encounter null. For each of traversing the linked list, we have a special list in which we have the head node with pointers to directly to the nodes of the linked list. Such a type of list is called as traverse list. Here searching is straightforward. We do have other type of linked list known as circular linked list, double linked list, multi-linked list. The main essence in the circular linked list is all the nodes are maintained in a circular fashion. That is, in the case of single linked list, the last node address, the link value is null. But now it will not be like that. It will be the address of the top node in the linked list. Of course, incidentally, if it is a circular list, there is no concept of top node or head node, etc. However, I am just trying to explain that in the case of single linked list, we have the last node where the link value is null. But now in the circular list, we don't have such a type of list at all, such a type of node at all. The one which is having its link value as null, you don't find at all. So all the nodes will be definitely having a meaningful link value. Such a type of list is called as circular linked list. They are also used practically in many applications. The double linked lists are the ones which contains links to the next node and also to the previous node. Whereas in the single linked list, the pointer or link is available for the next node only, not to the previous node. So double linked lists are used in some applications, which we'll be knowing in detail. Multi-linked list. They may contain more than one links in each node. We do have another type of linked list, which we can call them as a complex linked list. For example, to represent sparse matrices, also to represent the graph information in adjacency list fashion, and also for garbage collection, etc. We use special type of linked list, which we'll be discussing in detail in the coming lectures.